Welcome to the solution to the work, power, and energy problem set. Problem number 11. Let's read the question here and then talk about it conceptually before we get started. A 2-meter long pendulum is released from rest when the support string is at an angle of 25 degrees with the vertical. What is the speed of the bob at the bottom of the swing? All right. As we get into problems in this unit, one of the difficulties that you're going to have is distinguishing between, okay, what approach do I take to solve this problem? Do I use the work energy theorem? Do I use conservation of energy? How do I know which approach to use? What I would say to you is that when you read a problem, if there's not friction in the problem, and there's not in this problem, because it's assumed to be no air resistance, and there's no other indication here that there's any friction. So when you have a problem in which there's no friction, the first thing that you want to look at as a possible solution is conservation of energy. If there is friction in the problem, your hands are tied and will only be able to use work energy theorem to solve that problem. Frictionless, you could be actually using either, but you first want to look at a possible energy conservation solution. If the problem has friction, then you're definitely only able to use work energy theorem. All right, so no friction in this problem, so we know that we're going to use conservation of mechanical energy. So we start off with a conservation of mechanical energy statement in which EO, the initial mechanical energy in the system, is equal to the final mechanical energy in the system. This, of course, where the pendulum is now, is its initial state, and at the bottom of the swing will be its final state. So we ask ourselves, what kind of mechanical energy, or what kind of mechanical energies exist in this system in the initial state? We're told that the pendulum is released from rest, so that means it's not moving, therefore has no kinetic. Next, so we cross that off. Next we consider, is this object at a height above a base level in a gravitational field? And the answer in this question is yes, because we're going to use the bottom of the swing as the base level, and that pendulum starts out at a height h above that base level in a gravitational field. So we know we start out with gravitational potential energy, so we start out with a formula for gravitational potential energy, and because that's the initial state, we would call this distance between here and here the initial height. Okay? We write down the equation for gravitational potential, mgh, in this case mgho, and that's it. We've considered both forms of mechanical energy. It only possesses gravitational potential in the initial state. What does it have in the final state? Is it moving? Answer is yes. So we write down the equation for kinetic energy. Is it at a height above a base level in a gravitational field? The answer is no, because we established the bottom of the swing as the base level at which the height would be 0. So here h equals 0. So now we're ready to proceed. You can see in this type of solution that the mass cancels. It's in both terms. So we can cross that off. And we're looking for the speed. We know g. The only thing we don't know is h. Okay. So now we'll go to the diagram and see how do we determine that initial height. We know that this angle is at 25 degrees, as given in the problem. And we know that the length of the pendulum is 2 meters long. We also know that it's 2 meters long at the bottom of the swing. So, if we extend that initial height over, the initial height becomes the difference between the 2 meters from the top to the bottom of the swing and the green leg of the right triangle that I just labeled with an arrow here. So that means HO is equal to 2.0 minus the length of that green leg. Well, how would we find that green leg? Well, if we know the angle is 25 degrees, marked where I marked it in blue, and the hypotenuse of the right triangle is 2 meters, what side are we looking at to find here compared to the angle? And that's the adjacent side. So we know that we'd use the cosine trig function to find that leg. And that, of course, would be 2 meters cosine of 25 degrees. So HO is 2 minus 2.0 cosine 25 degrees. We go ahead and calculate, and we get an HO value of 0.187 meters. We're going to carry that out in extra digits and not sig figure ourselves. All right, we're ready to proceed. Substitute 9.8, 0.187, 1/2 v squared. Go ahead and take whatever algebra steps you need to solve for v, remembering eventually to take the square root of both sides. Calculate, pause if you need a moment, and you should get an answer of 1.9 meters per second. All right, we're doing this set of problems kind of out of order from what's on the problem set. And tomorrow in class, you'll have more practice with determining whether or not you use a solution that's work energy theorem or conservation of energy when we do numbers 9 and 10 in class tomorrow.